To understand MoE, you first need to understand the problem it solves. Traditional dense models, Llama, GPT-3, every standard transformer have a fundamental rule: for every single token they process, they activate all of their parameters. A 7 billion parameter model computes through all 7 billion weights for every token. A 70 billion model uses all 70 billion. Every single token. This creates a direct, unavoidable trade-off. If you want a model that knows more, that has more parameters, it must be slower and more expensive to run. Bigger model equals more knowledge, but also equals slower inference and higher cost. It's the iron law of dense architectures. MoE breaks this trade-off by splitting the feed-forward layers into specialized subnetworks called experts. Only a small subset of experts activates for any given token. The rest stay dormant. The big idea: you can have 100 billion total parameters but only use 10 to 15 billion per token. More knowledge without more compute. And it works surprisingly well. Let's get concrete. Inside a transformer, every layer has two parts: self-attention and a feed-forward network, or FFN. The attention layer stays dense, we don't touch that. It's the FFN where MoE lives. Here's how it works. Take a standard FFN and replace it with multiple FFNs, typically 8 in Mixtral, as many as 256 in DeepSeek v3. Each one is an expert. Then add a small learned linear layer called the router. When a token arrives at an MoE layer, here's the pipeline. First, the router computes a probability score for every expert. How relevant is each one for this particular token? This is just a softmax over the router's output. Second, only the top K experts get activated, usually K equals 2 for Mixtral, K equals 8 for DeepSeek. Third, each selected expert processes the token through its own FFN independently. And fourth, the outputs get combined, weighted by the router's softmax scores and summed. The math is surprisingly simple. The router says, this token looks like it needs the math expert and the code expert. Those two fire. The other 6 stay silent. Next token comes along, different router scores, different experts activate. And this happens at every MoE layer, for every token, hundreds of times per second. So what does this buy us in practice? Let me give you the numbers. Mixtral 8x7b has 46.7 billion total parameters but only 12.9 billion active per token. That means it runs with roughly the same flops, the same compute cost as a 13 billion parameter dense model. But what does it get you? On standard benchmarks, Mixtral matches Llama 270b, a 70 billion parameter dense model. So you're getting 70 billion quality with 13 billion compute. That's roughly a 5x efficiency gain. DeepSeek v3 takes this further. 671 billion total parameters, only about 37 billion active. It matches GPT-4 and Claude 3.5 Sonnet, the absolute frontier models, at a fraction of the cost. DeepSeek v3 cost $5.6 million to train. GPT-4 is estimated at over 100 million. And Qwen 2.5 MoE, 67 billion total, 17 billion active, matches its own dense 72 billion parameter variant with roughly 1/4 of the inference cost. This is the closest thing to a free lunch in deep learning. More model capacity at nearly the same inference cost. The parameters are there for knowledge, but they don't compute for every token. Let's tour the MoE landscape because it exploded in just over a year. December 2023, Mixtral 8x7b from Mistral AI. This was the breakthrough. Apache 2.0 license, ran on a single A100 or a Mac Studio with 64 GB of unified memory. This was the model that brought MoE to the masses. Before Mixtral, MoE was a big tech-only research curiosity. After Mixtral, anyone could run it. April 2024, Mixtral 8x22b. 141 billion total, 39 billion active. Near GPT-4 territory. March 2024, DBRX from DataBricks. 132 billion total, 16 fine-grained experts, top 4 routing. The first major enterprise open MoE. December 2024, DeepSeek v3. 671 billion parameters, 256 routed experts plus 1 shared expert, top 8 routing. And they trained it on FP8, the first model at this scale to use 8-bit training. Multi-token prediction. Auxiliary loss-free load balancing. This is the current state of the art. December 2024, Quen 2.5 MoE from Alibaba. 67 billion total, 17 billion active. The most practical consumer MoE, it's the size that actually fits on a single GPU with quantization. Notice the trend. We're moving from few large experts, 8 experts in Mixtral, to many small experts, 256 in DeepSeek v3. More experts means more specialization, and specialization is the whole point. This is where it connects to the quantization video. Before MoE, the local AI landscape was limited. In 2022 and 2023, your best options were 7 billion to 13 billion parameter dense models. Llama 270B, which was the best open model, needed 2A100 GPUs, roughly $30,000 in hardware. That's not local. After MoE, everything changed. Mixtral 8x7B at Q4_K_M quantization, which we covered in the last video, needs about 32 GB of VRAM. That runs on 2 used RTX 3090s, or a Mac Studio with unified memory, or a single data center card. The same model that matches Llama 270B now fits in a fraction of the hardware. Quen 2.5 MoE at Q4 runs on a single RTX 4090. GPT 3.5 class quality on a gaming PC that you can buy at Best Buy. Here's the formula. MoE multiplies model parameters without multiplying compute. Quantization divides memory requirements. Together, they're why you can run frontier-class AI on consumer hardware. One gives you the knowledge capacity, the other gives you the memory fit. They're two halves of the same revolution. Now, MoE isn't magic. It comes with real trade-offs, especially on the training side. During training, all expert parameters must be in GPU memory at all times, even when they're inactive for a given token. You can't free them. This makes MoE training memory heavy. The hardest problem in MoE is load balancing. The router is a neural network, and neural networks are lazy. Without intervention, the router learns to send almost every token to the same 1 or 2 experts, defeating the entire purpose. Researchers have developed several solutions. The most common is an auxiliary loss, a penalty term added during training that penalizes imbalanced usage. DeepSeek v3 pioneered an elegant alternative, dynamic bias adjustment, where they maintain bias terms that are adjusted after each step to encourage balanced routing, completely decoupled from the training loss. On the inference side, MoE shines for batch processing many user requests at once across your experts, but it has a memory wall. All expert weights must still be loaded into VRAM, even if only 2 activate per token. For DeepSeek v3 at 671 billion parameters, that means about 335 GB of VRAM even at 4-bit quantization, despite only 37 billion active compute. There's also a subtle issue with quantization. Different experts have different activation statistics. Standard calibration, where you collect statistics from a sample dataset, biases toward experts that get more traffic. You need per-expert calibration, which is an active area of research. Let's look at where the research is headed, because MoE is still evolving fast. The number one limitation is the memory wall. DeepSeek v3 has 671 billion parameters. Even at 4-bit quantization, that's 335 GB. Most people don't have that. Solutions are emerging: expert offloading, swapping inactive experts to CPU RAM or SSD and fetching them on demand, is being built into inference engines like llama.cpp and VLLM. It's slower, but it enables running models that otherwise wouldn't fit. Fine-tuning is harder on MoE. The risk of router collapse means full fine-tuning needs careful tuning. LoRa adapters need to be distributed across experts thoughtfully. And you can't easily merge experts back into a dense model. Distillation, training a smaller dense model to mimic the MoE, is active research. Looking forward, several directions are exciting. DeepSeek-style fine-grained MoE with hundreds of tiny experts instead of a few big ones. Multimodal mode, different experts specializing in text versus code versus images versus math. And Google DeepMind's Mixture of Depths paper from 2024 extends the idea beyond width. Instead of just routing tokens to different experts, route them to different depth positions in the network. Some tokens skip layers entirely. Tokens that need less processing take a shorter path through the network. It's MoE applied to depth instead of width. Here's the bottom line. MoE lets frontier quality models run on hardware you can buy at a consumer electronics store. That is not a small thing. The combination of MoE and quantization is the single biggest reason local AI went from a toy to genuinely useful in 2024. DeepSeek v3 proved MoE can beat dense models at the absolute frontier, and it did it for $5.6 million, not $100 million plus. Every major model release now has an MoE variant. This is the default architecture moving forward. If you're paying attention to where AI architecture is going, MoE is not optional, it's foundational.